Alright, so we're continuing to look at CSEC physics past paper questions. And in this video, we'll be looking at another question on atomic physics slash radioactivity. So this question comes from, let me see, May, June 2018, paper 2, question 4. Right, so paper 2, question 4, part A starts off by asking or telling us the 2011 Fukushima nuclear disaster raised questions about the wisdom of utilizing nuclear power. State 2 arguments for and 2 arguments against the use of nuclear fission reactors. So usually the primary arguments for the use of nuclear fission reactors are: 1, the amount of energy that fission reactions usually produce, especially when compared to, say, burning of fossil fuels. So a piece of information that essentially 1 kilogram of fission reaction using 1 kilogram of uranium-35 will basically release more energy than burning 2 million kilograms of coal, right? So once again, one main argument is the amount of energy that nuclear fission reactions produce, especially when compared to, say, burning fossil fuels. Again, also where fossil fuels are concerned, know that burning fossil fuels may release greenhouse gases like carbon dioxide into the atmosphere, and of course this will result in global warming and stuff like that. So another argument for the use of nuclear fission is the fact that no greenhouse gases, for instance carbon dioxide, is not released by nuclear fission reactions, and neither is sulfur dioxide, which can actually result in acid rain, right? So those are the two arguments for the use of nuclear fission reactions. Another argument, of course, is often that it is relatively safe, in that nuclear reactors are usually well constructed, and basically the chance of a disaster happening are very slim. But even if the chances are very slim, of course, we know of nuclear disasters, the most recent one being, of course, 2011 in Fukushima, and of course Chernobyl, right? So arguments against, of course, the primary argument against it is a potential risk in the event of some disaster, right? People will be exposed to vast amounts of radiation, which can cause devastating long-term effects. So arguments against, of course, you know that nuclear fission reactions produce a vast amounts of toxic radioactive material. So that's one argument against it. And of course, specialized facilities have to be built for the storage of these toxic radioactive waste products, right? Good. So that is part A of the question. Now, part B of the question goes on to ask or to tell us that nuclear fusion is seen as a great energy hope of the future. State 2 advantages of nuclear fusion over nuclear fission. So in the previous part of the question, we basically stated a few advantages, a few arguments for the use of nuclear fission, one of which was the amount of energy that it released, especially when compared to the burning of fossil fuels. So nuclear fission releases a vast amount of energy, especially when compared to burning fossil fuels, and of course nuclear fusion even releases more energy than fission. So that is one advantage of nuclear fusion over fission, right? So however, another advantage is that unlike nuclear fission, which produces vast amounts of toxic radioactive waste, nuclear fusion does not, right? So those are 2 arguments for the use of nuclear fusion over nuclear fission. But of course, even though the question didn't ask it, one drawback or one disadvantage, of course, would be the amount of energy that nuclear fusion reactors would need. And of course, no nuclear fusion reactor has been developed which essentially produces more energy than was actually used to operate it in the first place. And of course, in order for 2 atoms to fuse, vast temperatures, they would have to reach vast temperatures of the region of about 100 million degrees. And of course, those temperatures are not very easily attained. So that was part B of the question, right? Now, part C of the question shows us part of a nuclear fusion reaction, and we're basically asked to complete that reaction, right? All right, so I'll write down what is given. So what we have here is H21 plus H21. That produces, there's a space and there's a plus H11. Now, even if you don't do chemistry, you should know the symbol. The A symbol H is just represent the element hydrogen, right? Now, in another question earlier, we spoke about isotopes. And we said that isotopes are atoms of the same element having equal numbers of protons but different numbers of neutrons. So clearly what we're seeing is the same H, which basically means that they're representing the same element, hydrogen. So essentially these over here and this are isotopes of hydrogen. So this represents the atomic number or the proton number. So this is basically have one proton, the mass number is 1. So therefore this means that this has no neutron. So for this element we have a proton number of 1 and a neutron number of 0. So no, 1 proton, 0 neutrons. These on this side will basically have 1 proton, and because the mass number is 2, it means that the proton number of course is equal to 1 and the neutron number is equal to 1, right? So these are isotopes of hydrogen, right? Now, based on this reaction, whenever we have reactions like these, we say that mass must be conserved and the charge or atomic number must be conserved as well. What exactly does that mean? In terms of the masses, on the left hand side, if we were to add the mass of the reactants, we'll get 2 plus 2, which gives us 4. Which basically means that over on this side, the mass of the reactants must also add to give 4. So we take away 1 from 4, then that should give us 3. So whatever element goes here should have a mass number of 3. Now likewise, atomic number or charge must be conserved as well. So here we have 1 plus 1, 2 protons. And over here we must have a total of 2 protons as well. So therefore whatever element goes here will have 1 proton. Now we know that basically whenever elements have the same number of protons, it basically means that obviously they're isotopes of the same element, and therefore the same symbol H goes here, right? So basically what this fusion reaction produces is 2 isotopes of hydrogen. This one with 1 proton and no neutron is called protium. The syllabus doesn't require you to know that, but I'm just just stating it. This one is called protium with 1 neutron, 1 proton, 0 neutron, protium. This one is called deuterium, which has 1 proton and 1 neutron, and this one is called tritium, having 1 proton and 2 neutrons. And of course, we usually expect some amount of energy to be given off in the process because, as I explained before, nuclear fusion usually releases a vast amount of energy even when compared to nuclear fission, right? So we could put some amount of energy being given off as well. But of course, you wouldn't have lost a mark for that, given that they wanted basically you to fill this empty or fill this blank space, right? So once again, 2 isotopes of hydrogen fuse to produce 2 other isotopes of hydrogen, protium with 1 proton, no neutron, and tritium with 1 proton and 2 neutrons. So that's part A there. Part B of the question, sorry, that was part C rather, this is part D. Part D says a commonly used fusion reaction is this. So let me write down the reaction. So we have, once again, we have isotopes of hydrogen, but this time it's H21 plus H31 forming helium, and of course we have a neutron being released in the process. Mass number 1, 0. So, right, so we have this common fusion reaction where we have 2 isotopes of hydrogen fusing to produce helium, and of course a neutron is released in the process, right? So the table, it goes on to say that the mass of the reactants and products for this reaction are recorded in table 4 below. So we're given the mass of H21 in terms of its atomic mass units. We're also given the mass of H31, tritium, and also the mass of helium and the mass of the neutron, all in atomic mass units. And once again, I will remind you that basically, when it comes to calculating the energy which is released using equation E equals mc squared, m, which is the mass lost, must be in kilograms. So even if we basically find the mass lost and we express it in atomic mass units, we must then convert that mass to kilograms, right? So you don't need to convert all of these masses to kilograms first, because that will require additional work, which takes up extra time, right? So find the mass loss essentially in atomic mass units, then convert it to kilograms, and then put it into the equation E equals mc squared, right? So let's go ahead and see what the question asks us to do. So it says, using the information in table 4, calculate the energy release in this reaction, right? So I'm not going to copy the values from the table, but I'm just going to basically work out the total mass of the products, and I'm also going to work out the total mass of the reactants, and then we're going to basically going to what am I saying? Then we're going to find the energy given off, right? So once again, this is 2018, paper 2, question 4, right? So we'll find the total mass of the reactants. So of course, our reactants are what appear on the left-hand side of the equation, and our products are on the right-hand side, right? So the total mass of reactants equals, and of course we must always use all of these decimal places, all of them are important. So 2.014, 10178, 10178 plus, so that's the mass of hydrogen 2, hydrogen 3, 3.016, 04927. Right, and this of course gives us, suppose I have it on this paper here, that gives us 5.03, 015, 105. And this of course will be in atomic mass units, right? So the total mass of the reactants, these on the left hand side, will give us 5.03015, 105 atomic mass units. Now let's find the total mass of the products. So total mass of the products would be equal to the mass of the helium plus the mass of neutron, the neutron, which of course are given in the table as well in atomic mass units. So this is 4.002, 60325, plus the mass of the neutron, which is 1.008, 66492, right? And when you add that up, we get 5.011, 26817. That will be atomic mass units. So if we were to compare these values, we will see that there is a slight reduction in the total masses. So we went from 5.03015,105 atomic mass units to 5.011,26817 atomic mass units. Now when we looked at this equation, I earlier said that mass was conserved. But of course, when we're looking at this equation, we're talking about essentially what we call the large scale, or essentially the word I'm talking about, well, I would say macroscopic level, as opposed to this level where we're talking about all these digits, on all these, right? So at this level, there will always be a reduction in the mass. But of course, if we're just focusing on the actual mass numbers, then the mass will basically be conserved, right? So when we add this up, then we can now say that the mass lost, let's call that M, is equal to the total mass of the reactants, which is this. So the mass loss equal total mass of reactants, 5.03015105 atomic mass units, minus the total mass of the products. Oh, this is, yeah, 5.011,26817 atomic mass units, and that gives us 0.01, 0.01888 288 atomic mass units. So you have to be very careful in writing out all of these digits, because a little mistake will throw you off. But of course, you probably will not lose, a lot of marks for it, right? So that is basically the mass lost when this fusion reaction takes place. Now we want to find the amount of energy that was given off, or the energy given off, released in the reaction. So we're not finished as yet. So the next thing we must do is to basically convert the mass lost from atomic mass units to kilograms. So we know that U equals 1.66 times 10 to the minus 27 kilograms. And therefore the mass loss, or M in kilograms, equals 0.01888 times 1.66 times 10 to the minus 27 kilograms. And that gives us approximately 3.135 times 10 to the minus 29 kilograms. Right? So this is the mass lost in kilograms due to this new fusion reaction. Right? And having calculated the mass lost in kilograms, we can then use now Einstein's equation, E equals mc squared, to calculate the energy released, right? So this gives us E is equal to 3.135 times 10 to the minus 29 times the speed of light squared, which is 3.0 times 10 to the 8, and that's squared. And this gives us a value of 2.82 times 10 to the minus 10 joules. Right? So this is not exactly a vast amount of energy, but of course when we consider the fact that this is the amount of energy released by simply one atom of one deuterium atom and one tritium atom fusing, and of course one atom is so tiny, which basically means that if we're able to have an amount of material of this size, there'll be probably billions and trillions of atoms, which will produce even a greater amount of a vast amount of energy compared to an equivalent amount of say fossil fuel, right? So in this question, or in this part of the question, we're given a reaction and we're basically asked to find the energy released in the reaction. And in order to do that, we had to basically find the total mass of the products, total mass of the reactants, find the mass lost in atomic mass units, U, expressed in kilograms, and then of course use Einstein's equation, E equals mc squared, to calculate the energy released, and that would be in joules.